So we've seen how to calculate what you might call a theoretical probability at this point. And we looked last time at an example involving rolling doubles in Monopoly game. What if in the heat of the moment you can't really work out how you need to count all the different possible dice rolls and whatnot? What if you're just wanting some sort of estimate as to how likely it is that you manage to roll doubles and not lose the game? There's a few different ways you might try to answer that. I'm actually going to reference the way my sister used to play games when we were kids. So she was really bad about asking for a practice roll. And I thought it was ridiculous, but my mom thought it was cute, so it would happen a lot where she'd get the dice and she'd roll them, and she'd get something, and then she'd roll again for more practice, like you need practice at rolling dice. And eventually she'd end up rolling whatever it was she needed, and she'd try to claim that she was done practicing and she should get to keep that roll. That was my childhood. Anyway, so I kind of extended that as an idea as to what you might do. You take a whole bunch of practice rolls and see how often the doubles end up coming up in that practice set. Sorry, I have a really hard time not arching my eyebrow every time I think about that idea. But so, in that instance, you're no longer really calculating what you would call a theoretical probability. This is what we would generally refer to as an empirical probability instead. And instead of calculating that, our textbook likes to use the phrase relative frequency instead of talking about probability. But I like empirical probability just fine. So what we've done up until now was sort of theoretical. We didn't actually roll any dice. We were assuming everything was equally likely, the dice were fair, that kind of thing. Empirical probability, you're really getting your hands dirty, so to speak. In a classroom setting, I'll usually have a whole bunch of dice. Spoilers. I own many dice. Actually, these are my wife's, but whatever. And I'll give I'll give out a bunch of sets of dice, and we'll gather a whole bunch of data and see how often doubles end up coming up. It's usually not that 1/6 that we saw previously. Sometimes it's higher, sometimes it's lower. That's one of the dangers of live data gathering. The idea is that if you gather more and more dice rolls, so I usually have everybody roll the dice once and then look at the numbers of doubles. So we'll have some percentage that we end up working out. And it's virtually never, the 16.66666, that you would get, if from the theoretical calculation. And we'll talk about, well, why do the numbers differ? And somebody will suggest something about the dice being loaded, or every now and again somebody will complain about being unlucky, what have you. And then somebody else will end up getting around eventually to, well, we didn't really roll that many dice in the grand scheme of things. So, my classes generally don't get bigger than 30. That's not a really big data set. So what I'll then do is have people roll more dice, gather up those doubles data along with what we had before, and then compare. And generally speaking, it ends up getting closer to that, theoretical, 1/6 value when we go that route. So sort of the idea is what you'll often hear probability people, statisticians refer to as a law of large numbers. Though the general idea is if you gather more and more and more and more data, eventually those empirical numbers should end up more and more in agreement with what you're getting theoretically. So again, there's always kind of a risk that goes into it. I had one semester where like 40% of my students rolled doubles on the first go, and it was like, wow. I had another time where the percentage went up from, what it started at around 19% and jumped up to about 25. Like I said, sampling is kind of weird, and statisticians spend a lot of time trying to figure out how to make samples work. But that's kind of the idea that you'll see. Empirical probabilities end up being particularly important in scenarios where getting at a theoretical value is not really an option. So behavioral science, folks, so psychologists, sociologists, that sort of thing, they're often getting data that come back to them from survey responses, something along those lines. In that instance, they can't really, say for certain beyond the pool of people who took the survey. Generally speaking, though, they'd want to take that small data set and try to extrapolate outward to a bigger population, like a county or a nation, a particular demographic, what have you. So let's take a look at a particular example of this in action. And data. So this is a completely fictitious example I came up with, kind of motivated by an old computer programming textbook I had, whose authors seemed really fascinated with kumquats. So I interview some folks hypothetically as they come out of like the cafeteria on campus or something like that. And I've asked them two questions. One, are they a first year student, FY, or a continuing student? So, sophomore, up to senior, you get the idea. And then I asked them, which one would you rather do? Eat a kumquat or be poked in the eye? So here's the data. Again, completely made up. So assuming that we could take whoever we got out of the dining hall and then expand that outward, if we were to interview a random student, how likely is it that, say, they choose the kumquat over being poked in the eye? So I always like doing this because most of my students don't know what a kumquat is. One time I actually had a student bring one to me, before the test on this stuff. So, here's a kumquat, Professor Carroll. I learned something. That was fun. But anyway, so the idea here is roughly the same thing. Based on our data set here, how many people did we have who chose the kumquat? Well, we've got this column right here, 23 plus 84. That's what, 107 folks in total? So that's the number of people who picked the kumquat. We divide that by the total number of survey respondents we have. This is where that relative frequency thing comes in. So we add these two numbers and these two numbers together. Assuming I've done all my arithmetic right, that came out as 203. So this is starting to veer into the I'm not 100% comfortable with what this looks like as a fraction. So if you had taken this and turned it into a decimal, like I got 0.527 accurate to 3 decimal places, I totally get it. That's fine. On the other hand, what if we tried to figure out, how likely it is that, we picked out somebody who was a first-year student? Maybe you were trying to get a, handle on relative class sizes on campus or something. So same deal. In terms of, we still have 203 survey respondents to pull from, but on the other hand, now we need everybody in this first-year data column, or row rather. Rows usually run horizontally. Sorry. We want the 23 and the 79. We add them together. That should give me 102. And if I convert that, looks like a little more than 50-50, right? Because 102 would be half of 204. So yeah, I got 0.502 as a probability here. So that's the sort of thing that you might end up doing. I'll often do an example in class with how many of my students are wearing watches, and if we can assume that my class is representative of the student body at large, and then I just corral a random person walking across the quad and say, hey, you wearing a watch? How likely is it that it happens? So that's empirical probability versus theoretical probability. At this point, we've got the ground rules in place, essentially. We know how to calculate probabilities. We know most of the lingo. What we're going to be doing in the next section is kind of looking at some more advanced tricks or techniques, if you want to sound less sneaky, for how we might calculate probabilities. So keep on watching, or whenever you get around to watching. You get the idea by now.